What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock.
I have no idea. But anyway, just making sure that everything works here. We left off last time with DFS. We'd have fully covered DFS and BFS, and then we started considering applications to both of these basic search algorithms. And I did transition, right? Yeah, I transitioned. Anyway, we started considering applications to each one of these algorithms. All right. And one of them was, the basic one is, of course, connectivity. Given x and y, is x connected to y by some path in a directed graph or an undirected graph? And then we took a little bit of a digression talking about different types of ways that you can state the same problem over and over again. You can talk about decision versions, answering a yes or no question. You can talk about functional versions. If there is a path, actually output that path for me. A path, not necessarily all paths, but just, a path. And then you also have optimization versions, where you don't just want a path. Yeah, I know that there's a path there, otherwise I wouldn't have given this to you. I want to know what the best path is, according to some objective function. And one that I didn't mention in this discussion, but there's also, let's see, where are we? There's also There we go. I'll just add it as a bullet point here. There are counting versions. Right? So with respect to paths, what would you want to count? How many paths exist between those vertices? Right? How many unique paths exist between those vertices? And of course, if you've got a solution to the counting version, of course you have a solution to the decision version, because all you have to do is say, well, is it 0 or non-zero, right? If there are 50 paths, then clearly then the answer is yes. If there's 0 paths, then clearly the answer is no. But generally, those there may or may not be an equivalence between each one of these types of statements. Okay. All right. So let's go ahead and talk about another potential, application: cycle detection. Right? So, given a graph G, right? Does it contain a cycle or not, right? I.e., is it a acyclic, i.e., a tree, right? Just given the graph G, is it a tree or not, or a forest if it's a disconnected graph, of course, right? So what are some potential solutions here? How could you go about solving this problem? Here's a graph. Does it contain a cycle? What about DFS? Yeah, go ahead.
You can say if run DFS once
Okay.
for a node, and then see if at least one other node is still white.
Okay. Well,
Or not white.
that would be for disconnectivity, right? If I do a DFS on this section of the graph, and then there's still white vertices over there that I've not visited yet, then that would be a test for whether or not it's disconnected. That would solve that problem. Go ahead.
Well, you run DFS and you encounter gray vertices.
If you ever encounter a gray vertex, right? Then that means that implies a back edge, right? This is for undirected. And therefore implies a cycle. Good. What's another way that you could do this? Run BFS, right? And what? If you ever encounter a gray, or you won't be able to encounter it if it's undirected, encounter a gray vertex, it implies not a back edge in this case. Remember, there are no back edges or forward edges in the undirected case for BFS. Instead, it implies a cross edge, right, which implies a cycle. Right? So now let's think about the directed case. What's one way that you could do this? Don't worry about cross edges, back edges, forward edges. Right? How about asking two questions? One, does there exist a path x, right squig arrow? This didn't work last time until I put it in full math mode. There we go. And does there exist a path y, right squig arrow, to x? Right? If the answer to both of those questions for two particular vertices is yes, then what? Then there is a cycle, a directed cycle. Why? You can go from x to y, and then you can go from y back to x. What is that? A cycle. Now, of course, you would have to ask this question for what? For every single pair of vertices. So if I took this kind of naive brute force approach and asked the same question over and over again, then this would be, say, 2 runs of DFS, which is order n plus m. But you're doing it how many times? For every pair of vertices. Right? So ultimately, this one becomes order n cubed. Right? Again, why? Order n squared, I should say, times n plus m if you want to get technical. Right? So if you do have a lot of edges, DFS becomes a little bit, and you consider that like an edge traversal or an examination of a vertex, then M starts to take over, right? And then it could be as high as n to the fourth. Very, very inefficient. But it is a solution. It's a solution that already uses another solution. I'm trying to prime you here for later in the semester when we start talking about reductions. Reductions are nothing more than using one algorithm to solve another algorithm. You do this all the time when you do coding. You don't just write a function from scratch, right? You pull, you want to compute the quadratic roots of a quadratic formula, right? You don't write your own square root function, right? You call the square root function. And so you're using these subroutines to solve a different problem. You're using this algorithm over here as a subpart to solve this problem over here. And that's what a reduction is, right? Okay, another problem, bipartite matching, or not matching, but bipartite testing, right? Testing. Right? A graph G is bipartite if its vertices can be partitioned into two sets such that edges only connect between the two sets. In fact, when we write this, we usually call the sets L and R, right? Because we draw them as a left partition and a right partition. We'll come back to this over here. Let me go ahead and give you an example here. So here's my left partition with a bunch of vertices. Here's my right partition, maybe with a bunch of vertices. I'll just draw two here. And you end up drawing connections between the two partitions, never among them. So what I mean by that is, if I wanted to connect these two vertices right here, that's not allowed, right? Instead, it's allowed, but then it wouldn't be a bipartite graph, right? A bipartite graph is only when you can partition it into a left and a right partition so that they only go back and forth, okay? You can also talk about complete bipartite graphs. Complete bipartite graphs on n and m vertices means that there's going to be n vertices over here and m vertices on the right partition. And so, for example, let's just go ahead and go with K2. Actually, I'll kind of reuse this picture here. What does a K3, 2 look like? There are 3 vertices on the left. There are 2 vertices on the right. And every single possible connection is there, right? So you can come up with, statistics on, in a complete bipartite graph, how many edges are there, et cetera, et cetera, et cetera. Right? And it's just going to be n times m. Right? 3 times 2 here, that would have been, what, 6? Yeah. Okay. So bipartite testing, given a graph G, right? So given a graph G, is it bipartite or not? Right? So how are we going to solve this problem with just the tools that we have so far? Let's come back over here and let's make an observation. First of all, on that first one, are there any cycles? Are there any cycles in this example? Nope. So maybe it's bipartite if it's acyclic. Well, is this acyclic? Nope, but it is bipartite. Okay. What is it about those cycles, though? So here's one particular cycle. You go here, 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 and then back over here. I drew that, right? Yeah, right there. So I start at one end, go to the other. I have to form a cycle, I have to go back to the other one. I have to go back over here and then back over here eventually. So if I have to keep going back and forth, what can you extrapolate as the length of any cycle in a bipartite graph? It's always even, right? Because if you start in the left, you have to get back there, right? And so you have to go to the right and then come back at some point. Right? If you go back to the other partition, then you have to come back. Right? So it is a necessary and sufficient condition for a bipartite graph to have no odd cycles. Right? G is, or here's our observation. G is bipartite if and only if G contains no odd length cycles. Right? So remember, data structures and algorithms. Why do we like structure? It's because that structure can be exploited, right? And here's one structure. Here's one structure that doesn't even come from computer science. Here's a structure that comes from graph theory that we're now going to exploit. You can in computer science, you can exploit it, and a lot of difficult algorithms become suddenly easy if you restrict your attention to acyclic graphs like trees, or bipartite graphs like we're talking about right here, or some other type of graph that has a structure that you make an observation about and that you can exploit. In this case, right, general trees, they could have any cycle that you want, but in bipartite graphs, you have no odd length cycles. And it turns out that that's actually a really, really powerful structure that you can exploit for a lot of what are called NP-complete problems. NP-complete problems are extremely difficult in general, but if you look at a category of graphs like trees or bipartite graphs, suddenly they become easy. Yeah?
Wouldn't checking for this still involve the whole n squared times n plus n?
Maybe. We haven't even come up with a solution yet, have we?
No.
Nope. So let's talk about a solution. Given this graph G, how do I determine if it's bipartite or not? Well, let's go ahead and come up with a potential graph here. I don't know, do you care if there are straight lines or not? They look really nice when I do something like that. There we go. Okay, there's a graph. So first of all, tell me right off the bat, is this going to be bipartite or not? No. Why? What can you immediately see? 1, 2, 3. There's a triangle, which is a cycle of length 3. There's also a cycle of length 5 going all the way around the perimeter. Okay. Okay. So, highlighter. What I'm going to do is I'm going to start a DFS on this. But instead of the normal, or in addition to the normal white, gray, black colors, what I'm going to do is I'm going to color them one color when I first see it, and then I'm going to keep a kind of a flag value that when I go to the next vertex, I will use a different color. And I'm going to color its entire neighborhood that different color. Right? Then I'm going to go ahead and continue with my DFS and go to one of these, or this one, it doesn't really matter. And what I'm going to do is I'm going to flip it and use the other color, the original color here. So I'm going to look at this one's neighborhood, and I'm going to color all of its neighbors blue. But there's immediately a problem here, right? This one. Right? Do I color it red, or pink, or whatever this is, magenta, or do I color it blue? It's already colored magenta. So if I try to color it blue, I'm changing the color. What does that imply? That there's a cycle, not only a cycle, but what type of a cycle? An odd length cycle. Right? Why? Because check this out. If I just consider the cycle of length 4, right, and I alternate all the colors, then it will only be blue, and then I go around it basically. It'll be blue, magenta, blue, magenta, blue, magenta, blue, magenta. Right? That corresponds immediately to a left partition with these two, and then a right partition with these two. Right? But if you have a odd length cycle, like you do here, and I do this coloring trick, then there will be at least, oops, sorry. Change it to blue, blue. And then if I want to change it back to magenta here, there will be at least one where it has to be blue or it has to be magenta because its neighborhood has different colors. Right? So how could I modify DFS to do this? Think about the first discovery time of any vertex. When you discover it, look at its entire neighborhood. If whatever the color is of that particular vertex, if it's red or blue, you just need two flag values, right? Left or right, blue or red, right? And you color that current vertex blue, and then you color its entire neighborhood the other color. But you also check, as you color its entire neighborhood, if it's already colored that color, then you're fine. But if it is colored the same color as the vertex that you're on right now, then you know immediately that there's an odd length cycle. You can stop and say, this is not a bipartite graph. Right? Otherwise, if you get through this entire process and everything is perfectly colored and you have no blue adjacent to a blue, magenta adjacent to a magenta, then you know that it's bipartite. Now let's go back over here to this one. Right? You said that this was acyclic. Right? So is it odd cycle 3? It doesn't have any odd cycles, right? Why? Because it doesn't have any cycles, period. Right? So yes, trees are bipartite graphs. The only things that are not bipartite graphs are things with an odd length cycle, right? Because you can't partition those into two sets. You can talk about tripartite graphs, quadpartite graphs, or whatever if you want to, but we're not going to go that far.
So
Yeah.
For the one in the bottom, this wouldn't be a bipartite.
This is not a bipartite graph because you have a 1, 2, 3, 4, 5 length cycle. And this odd man out here would end up being colored both. Right? Or if it was colored blue, then it would be connected to a magenta. If it were colored magenta, then it would be colored. Then it would be adjacent to a blue. Right? So, again, no odd length cycles. All you need to do is perform a DFS and keep track of alternating colors. Right? Say red and blue. Right? If a red vertex is adjacent to a red vertex, it is not bipartite. Or a blue to a blue, then it is not bipartite. All you have to do is perform DFS and color them as you go. All right, the next one, and probably the last one for today, is going to be what's called a condensation graph. So I meant to look this up, and there are a lot of ways that you can collapse graphs, that you can expand graphs. There are a lot of graph equivalencies. Right? You can talk about isomorphisms. Right? So did you talk about graph isomorphism in 235? No? Okay. So what is an isomorphism? Let me go ahead and just give you a very, very simple example here. A, B, C, and, oh, sorry. I'm not done drawing it though. So X, Y, Z, there. Those two graphs are isomorphic. Why? They're the same graph. It's just a C3, just with different labels. So if you take a graph and you redraw it, but like you just move around the vertices, but you keep the same connectivity, you jumble up all of the labels, maybe use a completely different labeling system instead of ABC, you use alpha, beta, gamma, pi, whatever, right? Those are still the same equivalent graphs. Those are isomorphic graphs. Right? You might have, say, from grade school, right? Or maybe middle school or something like that. If you took a right triangle and you compared it to a right triangle that was just twice as big, what did you call those? You probably called them congruent. These two triangles are congruent to each other? Yes? No? Did you ever call them isomorphisms? No, that was too difficult of a word for junior high then. That's why they called them congruencies. Whatever. Anyway, there are lots of congruences, isomorphisms. But not only that, there are other looser ways of saying that this graph has the same structure as this graph over here. You can, yeah, go ahead.
Do all the edges have to be the same weight too?
Well, yeah, yes, but we're generally talking about unweighted graphs. And unweighted and undirected graphs, because it gets dicey when you talk about other types of niche graphs. Right? You can also talk about homomorphisms. Homeomorphisms, etc. Right? Each one of these preserves some structure. If I take one graph and transform it into another graph, some structure is preserved in that morphism. You're morphing the graph. And whether or not it's an isomorphism, a homomorphism, a homeomorphism, or any other kind of morphism that you can come up with, some structure is preserved. All right? My goal here, our goal, is to take a large directed graph and condense it into a smaller graph, but preserving, again, you need to preserve some sort of property or some sort of structure, preserving connectivity. Right? Now, it's pretty easy to do this in general. Right? For example, you can, I forget what it's called, expand or contract an edge. So for example, here's one common way of taking a weighted graph and transforming it into an equivalent unweighted graph. Suppose that I went from A to B and it was of weight 3. All you need to do, and then there's a whole bunch of other, edges all around, but let's just focus on this one edge. All I need to do is expand that out into 1, 2, 3 edges. Call this A, B, and call this, I don't know, x1, x2. And now, each one of these has an implicit weight of 1. Right? And what I've done is I've transformed a weighted graph, weighted directed graph, into an unweighted directed graph. So is the distinction all that important? No, because you can have this morphism between these two. This is called a contraction or an expansion. And you can do this even with undirected graphs and unweighted graphs if you want to. But this is just one way of doing it, right? Now, which one is better to deal with? One with more edges, or one with less edges but is weighted? More edges but unweighted, fewer edges but weighted. Right? Which one is more complex? Right? I don't know. It depends on your application. Our particular application here is going to be taking this graph and condensing it down from a 7-vertex graph into a smaller graph, but preserving connectivity. We're going to be preserving actually what are called strongly connected components. Right? So let G be a directed graph with, and let X and Y be vertices in G. We say that X and Y are strongly connected if there exists paths from X to Y and from Y to X. Right? Why do we say they're strongly connected? Because if I'm at X, I can get to Y. And if I'm at Y, I can get to X. Right? So in a network, whatever you're modeling, whatever your network is actually modeling, if it's like modeling an actual network, X can speak to Y, it can send messages to Y, and Y can respond with messages. But it may not be the case that they're strongly connected. X might be able to speak to Y somehow, right? There's a path from X to Y, but Y cannot respond to X for whatever reason, right? That there is no corresponding path backwards. It could be the case that neither one of them can speak to each other. There is no path from x to y, and there's no path from y to x, right? In which case they're not connected at all. Right? So what we want to do is we want to come up with what's called a condensation graph. A condensation graph collapses a large complex graph into its strongly connected components. So what is a component? A component is a subset of vertices, each of which is pairwise strongly connected. So if I've got A, B, and C, A can talk to B, B can talk to C, C can talk to B, B can talk to A can talk to C, C can talk to A. In other words, they all know how to speak to each other. Right? They're all strongly connected together. From any vertex in this group of three, I can reach any other vertex, and vice versa. Okay? So here is the algorithm. All right? You start with a directed graph. Right? And one, I don't know how this is going to come out, perform a DFS noting the finish times. Right. 2, you compute the transpose graph. Right. In other words, you simply reverse the edge orientation. Right. 3, you perform another DFS. Each time you start over, another DFS, excuse me, in order of finish time, right? From the original first DFS. Each time you start over, you create a new node, right? This indicates a strongly connected component. Okay? I'm 90% sure that's finish times. If not, we'll have to come back and say starting times. But in any case, right? All right. Okay. So here's our example. Let's do a DFS on this first. Okay. All right. We'll start. You can start arbitrarily anywhere that you want. I'll go ahead and start at A because that's lexigraphically first. Okay. I can make this a little bit bigger. All right. So 1. Right. And then, of course, you color it visited. Right. Where do I go to next? In my neighborhood, I see D, I see B, and I see E. Again, it doesn't matter how you proceed. We'll go in lexicographic order here. 2. And this is also going to give us some practice here on performing a DFS. That's been visited. Okay. Where do I go next? I see C and E in my neighborhood. So I'll go to C next. 3. All right. C, I see D. I see B as well, by the way, but it's already been visited, so we're not going to backtrack yet. I see D and I see F. Right. And remember, I don't see E because that edge orientation is this way. Right. Okay, so where do I go next? D. Okay. Now where? G, my only choice. 5. Okay. And finally, not finally, but next, F. F is discovered at 6. Characterize F for me. It's a sink, remember? With anything in a directed graph, you can have sources, you can have sinks, and this is a sink. So tell me, predict, what is this going to look like in the condensation graph with respect to F? From F, can you go anywhere else? Nope. So it's going to be its own strongly connected component. Once you're at F, you're stuck there. You're stuck in that sink. Okay? So we'll start backtracking here. 7, 8, 9, Once I get to C, that is finished, 10. And by the way, I've been marking them as done as I go along. Processed, right, done. Now I'm back at B here. Now what do I do? Go to E, a discovery time of 11. And because its neighborhood is done, I immediately go back as well. So visited and then processed. Processed, processed, and this is 13 and 14. Okay? Okay, that is my DFS on the original graph. Now what I want to do is I want to reverse the edges. I'm going to compute the transpose graph of this. And I'll just do that right here below. It's going to be the exact same vertices, A, B, C, D, E, F, and G. But all of the edges are now reversed. So this edge over here is going from D to A now instead. From B, we go to A. And from E, we go back to A. All I'm doing is reversing them. Why is it called the transpose graph? Think about an adjacency matrix. A goes to B. If I want to reverse that and say that B goes to A, what do I do with that matrix? You take the transpose of it. And that's why it's called the transpose graph. All right, I can go from C to B, but that one was there as well. I'll just reverse them graphically here. But otherwise they were connected to each other. F goes to G, back to C, D, there we go, up to B, and down to C. There we go. Okay. I'm pretty sure B. Done, C. Okay, yeah. So now what we'll do is we'll perform a DFS, but instead of in an arbitrary or an alexicographic order, we're going to do it with respect to the finishing times from up here. In ascending order, descending order, I think that either one will work. Yeah. And then each time we start over, it's a new node. All right. All right, so let's go ahead and start doing this. First of all, we'll go ahead. We'll go ahead and go again. I should have looked this up before I came, instead of doing it just from memory. We'll go ahead and try it. Start it in A. Right? 1, and then in fact we don't even need to do the timestamps here at all. We just need to make sure that we start over. Right? All right. So what happens at A? There's nowhere to go. Right? It's a sink. Right? So A is its own component. Okay. And it's our that's also done. So I'll just go ahead and mark that as purple there. Right. Now let's go ahead and start over at the next one, which would be B. Right. From B, where do I go next? C. Okay. Here we can go during this DFS. We can go in lexicographic order. Otherwise, you can go in reverse order like we were doing here. This is 13. I could go, my only choice here would be to go to A, but of course that's already been processed, so that's not really a choice. And then my only other choice here is C. So C gets discovered. At C, I could go back to B, but it's been discovered, not processed. And my only other choice here is to go to E. At which point I start backtracking. There we go. Backtrack. There's no other option here at C, and I backtrack, backtrack. B, C, and E, right? I would have to start the DFS over at this point. So B, C, and E are all one component. Now look at the original graph. From B, I can get to C. From C, I can get back to B. So those are strongly connected. B goes to E, E goes to C, C goes to B. right? So B can go to C, and C can eventually get back to B, right? Take any two combinations out of this strongly connected component, and you can find a path between them. All right, next. Where do we start next? D? Yeah, D. Right. Now from D you can get to C, but that's already been processed. A, you can get to A, but that's already been processed. So you go down to G. At which point you reached a dead end. You start backtracking, and you find that D and G are part of a strongly connected component. And then, as we predicted, F is all on its lonesome down here. You'll start a DFS there, but unfortunately that's where the DFS ends. Okay? Now in your DFS, we said that you could go from D to A, but you can't go from A to D. So what we could do down here is draw some additional edges. From A, in the original graph, from A, where can I go? I can go over to D, or I can go to the strongly connected component that contains D with respect to the condensation graph. Or I could go to B, or I could go to E, but guess what? That's already taken care of by collapsing these down into one strongly connected component. All right? From B, where can I go? Well, I can go to C, I can go to E, and I can always get back there, but where else? From C, I could go to F, and from D and G, I can go to F. Right? This is condensed. Right? So you see why it's called condensed now? We condense it down into its strongly connected components.
Are you looking at the original graph?
Yes, because that's what you want to preserve. You want to preserve the connectivity of the strongly connected components of the original graph. Tell me about this graph, by the way. Do you see any cycles in it? Nope. Why not? What if there were a cycle here? A, B, C, A, B, C, A, B, C. I can go from A to B, I can go from A to C, but also I can go from C to A, and I can go from C to A, then to B. Cycles collapse. Cycles condense down into a strongly connected component. Right? So what you result here, ultimately the result, the result is a DAG, a directed acyclic graph. Right? Acyclic. Why do we like acyclicity? Because it takes out, a lot of the, it puts in, I should say, a lot of structure. That's why we like trees for data structures, right? There are no cycles, so you're never going to get caught in this loop, ever. Right? So we like trees because they are acyclic. We like DAGs because they are acyclic. And it removes a lot of redundant information. Right? If you want to simplify a network and say that all these people, they talk to each other, right? All you need to do is tell one of them, and the rest of them will broadcast it to each other, right? If you want to go back to your social networks, right? You only there's a Simpsons episode, old Simpsons episode, where they have a rumor that they want to tell, or some gossip that they want to tell, so they pull out the phone book and they start at the very first name, Apple or something like that, and then they call that person up, and then there's a flash forward, and they're at the end, and they call the last person in the phone book, Zebra, and then the joke is, those two are the biggest gossips in town. We only had to call those two, not the entire phone book. And why? Because they're part of a strongly connected component that eventually got around to everybody else. All right, so that's strongly connected components in a condensation graph. By the way, if everything was reachable, what would it look like? It was like if you had, if every vertex in the original graph was strongly connected, if every pair of vertices were strongly connected. Like if it was just one big cycle, what would the condensation graph look like? Just one node, right? What if you ended up with a condensation graph that was exactly equivalent to the original graph? It's already a DAG, right? So lots of questions that you can answer about this by just producing a condensation graph. Right? Do you get a smaller graph? No, it's exactly the same graph that I started with. Then it was already a DAG, right? All right, so questions? Yeah, go ahead.
Should BCE be connected to BG in the original graph?
Oh, probably. I think I missed one. So from D, you can go to F, and you can go to G. Where else? B. From B, you can go to G. There we go.
Oh, yeah.
There we go. Thank you. It's still a DAG. Why else do we like DAGs? They are a topological order, or they are a poset, right, from 235. And if you've got a poset, then you've got all these other structures. They're reflexive, they are antisymmetric, they are transitive, right? Cool?
So
Yeah.
basically, if it goes from one input to one output, that's the condensed graph pretty much already.
Yeah, if you start out with the DAG, in fact, here's the here's the largest DAG that you can have. It's called a tournament. And all the vertices are here that are available. There we go. There is a tournament of size 4, I guess. Did I get them all? Oh, I need this one. Everything should have, so 1, 2, oh, I already have, I've got a redundant one here, sorry. This one doesn't need to be there. 1, 2, 3, 1, 2, and then 1. I got them all there. There we go. That's a tournament. Why? Because if you've got a tournament, like a last man standing tournament, right? A defeats B, right? And for the winner up at the top has to defeat everybody, or has to defeat them through transitivity. If A beats B, B beats C, then by transitivity, A beats C, right? And they eliminate them. At least that's the idea. Now here, in like a real sports event, if, okay, so yeah, let's go with Big Ten then. Who beat Iowa? Was it Purdue? I forget who was it that beat Iowa? No, it was Illinois, right? All right, so Illinois defeats Nebraska, right? No, this is going to be about, if I involve Nebraska, I'm not going to be able to get Nebraska defeated. Blah. All right, well, next week. Suppose Nebraska defeats Purdue next week. Purdue defeats something. We should be able to defeat that something because we defeated Purdue, right? But football doesn't work that way. Yeah. Any given Sunday, right? Or any given Saturday or Thursday or sometimes Monday, right? Any football team can win any game. It all depends, right? So that's why this is more of like a round robin tournament. But in any case, not to get off the rails here, this is already a DAG. This is already a tournament. And if you started out with this, you would end up with exactly the same thing if you condensed it down, because it's already a DAG. Right? Yeah?
So instead of doing like, make a condensed graph, if we just found all the cycles and then we like collapse the cycles to one node, wouldn't that do the same thing?
Yes, but then you have cycles within cycles. And then you can take this cycle and go around, think of a figure 8, right? Here's one cycle, and then I'll tack on another cycle into that. You want both of those condensed down into one. So you could do this over and over again. Found a cycle, collapse it. Found another cycle, collapse that, collapse that. This is, I don't know how many times you'd have to do that over and over again to find cycles. This one gets you there right away. Right? You'd basically be doing the same thing. All right, then the next way that we can take a graph and condense it or give an equivalent graph under some morphism is going to be with a minimum spanning tree. Right. And for this, we'll go ahead and start next time. Basically, you have a weighted graph, given an undirected connected weighted graph. You want to find a tree that spans it of minimum total weight. Basically, you have this complex network. You want to condense it down into just the backbone of the network, the strongest backbone, so that it looks more like a skeleton rather than all these interconnected things, all these cycles. We'll take those cycles and throw them out and only leave a tree, which is acyclic, but that tree will consist of all of the edges that give you the minimum weighted tree that still touches the entire graph. Right? We're going to look at several algorithms here, and it'll give us a nice opportunity to introduce a brand new data structure called the disjoint set. Right? Tree-based still, but it's kind of cool. Kind of cool, but it's also extremely limited. I've not found any other application to this thing other than minimum spanning trees. So, oh well. But it's still kind of cool to look at, and it gives us some more Python practice if we want.